let's dive in and get started. Most of you have I think all of you have probably been here before. I'm Dave from Saturday Morning Astrophysics at Purdue. And this morning we have some intelligent, good-looking TAs, teaching assistants with us who will monitor the breakout rooms. They'll introduce themselves as we get started with breakouts. And we have our guest of honor who will be presenting the topic of the day, gravitational waves and multi-messenger astronomy. And his name is Professor Matthew Wiesner. Matthew, do you want to give us a quick hello?
Hello.
So Matthew has done a variety of SMAPs over the years. He's been with us about every year. In fact, Matthew is the originator of SMAP. Matthew and I talked about doing something. It was his idea when he was at Purdue as a postdoc. He's now a professor at Benedictine College in Lisle, Illinois. But Matthew and I talked one day and we came up with a way to implement his idea. And here we are 7 years later with SMAP going strong. So we have a short presentation and then an activity. We're going to have you go into a breakout room and do a really cool activity where you're going to learn about some fascinating things. So I won't give the story away now. I will turn it over to Matthew and say, Matt, shall we go ahead and get started?
All right. Thank you very much for the introduction. It is a pleasure to be here to see everybody. I'm going to share my screen. Okay, good. So I'm going to talk about gravitational waves and multi-messenger astronomy. So can you find the feature on your screen that gives a thumbs up, or you can just give a thumbs up? How many people have you heard? How many people have heard of gravitational waves before? Okay, so many of you have heard of gravitational waves. They've been big in the news, lots of things going on with them. All right, so what I want to talk about is these things. How do we learn about things in space? What gravitational waves are? How we try to find objects that produce gravitational waves and light. We call these kilonovae. And how do we tell a kilonova from a supernova? All right, first off, who I am. So as Dr. Sederberg said, I'm a professor at Benedictine University in Lisle. So this is Chicago. Here, Lisle, Illinois is right here. So it's a little bit west of Chicago there. This is one of my favorite books. This is what I read when I was a kid. I got this book for free and just spent lots of time reading it. So I got really interested in astronomy by reading books when I was a kid. So I still love talking about space. These are some colleges that I have been to. Of course, before Benedictine, I was at Purdue as a researcher. And this is a picture of me. I got to visit the Paris Observatory, this really old observatory in Paris. This is one of my, it was really fun getting to do that. All right, so here's a question for you. Let's say you have a dog and you want to know what your dog is doing in a different room. You're sitting in here, you're at Saturday Morning Astrophysics, and you're trying to figure out what your dog is doing. So you're not in the same room with the dog. What is some way you could learn about what your dog is doing? Could somebody unmute and tell me, how do you figure out what the dog is doing?
Ask your parents what exactly they're doing, or ask someone in another room exactly what they're doing.
Okay, so ask your parents, ask somebody else that has information. That's a good one. So let's go through some options. So one thing you do is listen. You could listen for the dog. So you could hear, oh, there's like scratching or barking or something like that. So you're getting some information from listening. Or you could look, you could like peer around the corner and say, oh, I see what you're doing. Or you could do both. You could do both. You could listen for the dog, and you could peer around the corner, and you could ask your parent, hey, what's my dog doing? And now you get lots of information. They're like, oh, he's playing with this ball. Like, that's okay, good. Like, oh, he's chewing up your shoe. Oh, that's bad. We need to go deal with that right now. So you're getting information about what's happening in the next room. And there's several ways you could do that. So that's what we're talking about today. We're not talking about puppies. Puppies are very cute, but we're talking about stars and things in space. So here's the same question, but asked about astronomy. How do we learn about things in space? Who can give me an idea for that?
We learn about things in space by building new technology, larger telescopes, and like the James Webb space thing that just launched recently. So to get information like radioactive and waves and images of space.
Okay, very good. I'm glad you've been thinking about the James Webb Space Telescope. So we build new telescopes. That's one way to do it. And so we're getting some kind of information there from what we call electromagnetic waves or light. But there's other ways. There are also other ways to do this. Let's here. Okay. So one way is light, like you just mentioned. We can use light. There's lots of different kinds of light. You may have seen this in school already, that there's visible light, the stuff that lets you see me right now. There's infrared radiation. That's primarily what James Webb is going to look at. There's radio waves, there's gamma rays, there's X-rays. There's lots of different kinds of light. And this is a telescope down in Chile that uses light. But there's other ways, just like with the dog. You could see the dog, you could hear the dog, you could ask the parents about the dog. There's different ways of getting information. There's also different ways of getting information about things that are happening in space. So we can use light, and that's a lot of the things we do. But we could also use things called neutrinos. Neutrinos are little particles that come from things like the sun and from other galaxies. And we can, if we catch those, we can get information about what's going on. And another way is gravitational waves. These waves that travel through the entire universe, we can learn about things that are happening without ever getting the light. So the challenge is to find an object where we can study it using more than one messenger. So by messenger, I mean like light. So you could use like light and neutrinos, learned about supernovae in that way. You could use light plus gravitational waves, and you get more information. Just like rather than just listening for your dog and trying to figure out if your dog is chewing a ball or chewing your shoe, it's better to listen to the dog and go look. You get more information and you can better figure out what the dog is doing. In the same way, we can get a better idea of what a star is doing or some object is doing if we get more than one piece of information. So that's what we call multi-messenger astronomy. That's that big word I had in the title. We can use more than one thing to learn about what's going on. All right, what's a gravitational wave? So here's a picture. This is a simulation of gravitational waves. These are supposed to be two black holes that are spiraling into each other and then colliding. And when they do that, they produce these ripples in space-time. And it might seem kind of weird, but it's not that much different than if you took a rock and you threw it in a lake and you see the ripples go out in all directions. It's the same idea, except these waves aren't just in a lake. They're going through all of the universe. They're going through all of the universe, including the Earth. That's what we call gravitational waves. So when something big changes, like when really massive things hit each other, that produces gravitational waves. All right, this is a question for you. Who knows what a black hole is? Grant.
A black hole is it's when a sun or something else becomes incredibly dense and it forms into a black hole, which sucks in all matter around it, including light.
Very good. That's a black hole. Megan, what?
Like a black hole is when a star dies and it becomes extremely dense cosmic body where nothing can escape, like not even light can escape.
Exactly. Good. So you've already, I don't even have to say much about this slide. Many of you already know about this. So black hole is a place where gravity is so strong that even light can't get out. So this was a picture that came out. A lot of astronomers put a lot of work into getting this image of a black hole. And so you can see this is a cartoon of it. This is the actual picture. So you can see this stuff, this gas that's spiraling around what we call the event horizon, the place where once it crosses that, nothing can ever come out, including light from that. So we learn about a lot of black holes, and gravitational waves let us study black holes, especially black holes that are running into each other. All right, a neutron star. I'm going to mention neutron stars. A neutron star is a really, really dense core of a star. So it's what's left behind after a really massive star collapses and explodes. So here's the size of the Earth. Here's the size of a type of dead star called a white dwarf. And there's the size of a neutron star. Neutron star is about the size of a city. So it used to be this really massive star, and now it's about the size of a city. So it's not as dense as a black hole, but it's really, 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 really heavy. All right, so how do we find gravitational waves? That's the next question. We've learned that we can learn about things in space using light and gravitational waves, and that's our goal. How do we find the gravitational waves? Well, there is a facility which is called LIGO. LIGO is an acronym for these big words: Laser Interferometer Gravitational Wave Observatory. And each of them has 2 interferometers that are really long. So there's these 2.5-mile long arms. There's one of them in Washington State and one of them in Louisiana. And there's a third one in Italy. There's a third one called Virgo in Italy. And these things can measure gravitational waves. When these waves go through the universe and they go through the Earth, they can measure this very slight shift in the size of the Earth. And then they also can check if they both get it at the same time or right after each other, they can get information about those gravitational waves. So the first gravitational wave was found not that long ago, in 2015. In 2015, so about 7 years ago now, the very first one was found with LIGO. By now, we found about 50. The first one was in 2015, and by now we've gotten about 50 gravitational wave events. And so how many have both gravitational waves and light? These are all the gravitational waves of events. Not all of them also, we were able to find light from them too. It's only, so we did find one of them that produced both gravitational waves and light. And that's what we call a kilonova. When you get something that produces both gravitational waves and light, that's what we call a kilonova. And we found one in 2017. And that was when 2 neutron stars, these things I just talked about, these really dense cores of stars, when 2 neutron stars collided with each other, they produced gravitational waves, that's like this, and they also produced light. We found them in a galaxy that's pretty far away from Earth. So why do they produce light? Well, this cartoon gives an idea of why that is. You have these 2 really, really dense cores of stars, and when they hit each other, they just light up. They go through what's called nuclear fusion. They have these nuclear reactions at a really, really high rate, and so they glow at different parts of the spectrum. You get bursts of gamma rays, you get bursts of visible light. And so when this happened in 2017, what was that, 5 years ago? Now, almost 5 years ago now, we were able to see the gravitational waves. LIGO saw the gravitational waves, and then astronomers went and started searching for where LIGO said to look, and we started looking for things that were new. We started looking for things that were new in the sky to see if we could find the light from this event. And this was our first chance to do with this multi-messenger astronomy. All right, this is what it looks like. This is one of the students that has worked with me. Her name is Zoya. She's on her way to become a medical doctor. But while she was at Benedictine, she helped me do some of this research. And this is what it looks like to actually be doing this work. So notice this is, I'll talk about the spectrum in just a second here. She's looking at a spectrum here. This is over here, this is showing what the instrument on the telescope is in Chile. The telescope is down in northern Chile near the ocean. And you can see she's zooming with the person who's on the mountain. This person is on the mountain in Chile and doing things with the telescope, but we were at Fermilab. Has anyone here heard of Fermilab? Have, okay. Some people that have heard of Fermi. It's near Chicago. It's what's called a particle accelerator. So this is at Fermilab. So notice there's all these different screens. We're getting different information about the objects that we're observing. Even though the telescope, we're running the telescope remotely. Just like I'm giving this talk remotely, we were running the telescope remotely. And the other thing to notice is all these snacks. Notice that astronomers stay up all night doing this stuff and we get really tired. And so one of the things that helps is to have some snacks. There's some cookies there. I think there was some candy in there, with some popcorn, lots of unhealthy snacks that we eat to help keep us up at night. When we're in Chile doing observing, they'll actually bring us lunch at night. They make us lunches, and at 1 a.m. we go and eat our night lunch. So it's kind of nice, and get our coffee. It's nice to help us stay up at night so we don't fall asleep while we're observing. All right, so the next question. Yeah, snacks are always critical. I agree. When one of the issues that's going to come up is we are looking for new objects. We're looking for new things in the sky, but there's more than one reason you can get a new thing in the sky. And so we have to be able to tell, is this new thing actually the colliding neutron stars that we were looking for? Is it actually, after they tell us there was a gravitational wave, we go looking for the new object. Is that new object really a kilonova? And so to do that, we have to use a spectrum. Can anyone tell me what a spectrum is? How many, let's go for this. How many people, who here has ever heard of a prism?
With a prism, if you shine sunlight through it, it splits the colors of the rainbow so you can see all the colors.
Exactly. So just like this, you can get a prism, you shine light through it, it splits the colors up, and you realize that what looked like white light was actually made of different colors of light. You could say in physics, we say different wavelengths of light, but these are different colors of the spectrum, and you can only see that after you spread the colors out like this. That's looking at a spectrum. That's, if you do that, you're looking at the solar spectrum. This is another way of looking at the solar spectrum. Raindrops can act like little prisms and spread out the sunlight into the different colors. So these are, you've seen this before. You've seen rainbows. You've seen that's what a spectrum is. You take the light, you break it down into its colors. And so we do that same thing with the light from an object in the sky. Now, there's three different types of spectrum you can get. One is a continuous spectrum, which a rainbow looks like a continuous spectrum. I have just a whole set of colors going from red all the way over to violet. There's also this thing called an emission spectrum, where you have just specific colors. Everything else is dark. And then there's an absorption spectrum, where you have just dark lines. And this is what, if you look on the right, these are graphs of those colors. So these are things on the left are what you would actually take a picture of. You could actually go out and take a picture. On the right, these are graphs. So this at the top, this is what we call an absorption spectrum. Notice I'm graphing how bright it is versus wavelengths. And so that corresponds to this one on the bottom here. So notice that it's really bright, but then there's a dip. And then it's really bright, and then there's a dip. It's really bright, and there's a dip. That's what's called an absorption spectrum. And we can correlate that to particular elements. When you learn, as you learn more chemistry and physics, you'll learn how to correlate that particular dip to a particular element. And so we can say, oh, well, that's silicon right there, and so on. This is an emission spectrum. Notice that it's all dark, except where there's a bright light. And so that's what a graph of this would look like. And then lastly, we could have a graph of a continuous spectrum, where there's no dips and no bumps. It's just a complete smooth curve. But notice it has this kind of weird shape. And that's, there's a reason for that. I won't go into right now, but the continuous spectrum looks like this. All right, so what we know is that a kilonova is going to look a lot like this. A kilonova is going to look a lot like this. It's not going to look like the previous two. It's going to look a lot like this one. And so this is a spectrum of that kilonova that we found in 2017. And notice it looks pretty similar to that continuous spectrum curve. There's a little bit, there's like some noise in here, but there's not the really distinct dips or peaks like there were before. It basically is a smooth continuous curve. That's what the spectrum of a kilonova would look like. All right, almost done here. Does anybody know, has anyone ever heard of a supernova? All right, let's see, Megan, can you tell us about a supernova?
Supernova is like a stellar explosion when two neutron stars probably collide and it bursts.
Yeah, I see a hand up from Kindle. I'm betting, can you go ahead? I don't think it's listing your name, but
is when a star explodes and usually forms into a black hole, but I don't know if it's for sure.
Good. Daniel, go ahead.
It's when it's when a star gets to a certain point in its lifetime where it'll explode, and depending on its mass, depends on what it'll become.
Good. Alicia? Or sorry, Greta.
A supernova is when a star comes to the point in its lifetime where it goes through stages what leads up to the supernova. If it's a large enough star, which the supernova is when the star certain particles react with each other because of what's happening when it gets older, and then that causes the reaction of it exploding and then turning into something else, such as a black hole or a dead star, basically.
Exactly. Very good. Very good answer. So again, you already know the answer. A supernova is an exploding star. It's often a star that is very massive and got too old and collapsed, and it explodes. So it's just one object that gets too massive and it explodes. So that's different from a kilonova. A kilonova, remember, that's that we said is when two neutron stars spiral in and explode. But a supernova is when a single star explodes for some reason. So here's a simulation. This is a simulation of what's called a type 1a supernova. So that's when there's a white dwarf that gathers too much mass and gets too massive and blows up. So you're going to see it, the shock wave going through it. There it is. It blows up and gives off a huge amount of light. So notice this gives off this huge amount of light. So this would be a transient too. This is not what we would be looking for. After we get the gravitational wave signal, we would be looking for a kilonova, but these can happen at the same time. And by looking at the image, you can't tell the difference between a supernova and a kilonova. They'll both be really bright and new things. So to tell the difference, we need to use a spectrum. All right, these are the two main types of supernova. This is a type 1 supernova where you have a star like the sun that goes red giant, sheds its outer layers, the white dwarf is left behind. But if it gets more mass from some other object, it can explode. If it gets too big, it can explode as a type 1a supernova. Or you can have a really massive star that's more than about 8 solar masses, so a really big star. It goes into the red giant phase and then collapses when it can no longer make new elements. It collapses and explodes as a type 2 supernova. So there's slightly different mechanisms that produce them, but the commonality for supernova is they're stars that explode. All right, if it's a supernova, we want to classify it. So we need to be able to tell the difference. When we look at an image and we find an object, we need to be able to tell, is it a supernova or is it a kilonova? And then if it's a supernova, we want to classify it. This is a decision tree that tells us how to classify it. We look at the spectrum and then we say, is there hydrogen? If yes, it's a type 2. If no, it's a type 1. and then we can further subdivide it from there. These are some spectra of supernovae. I showed you the spectrum of a kilonova. It was that continuous kind of smooth curve. These are spectra of supernovae. So here's the spectrum of a type 1 supernova. Notice that I see a bunch of different lines here. These are these dips, these absorption lines, but I don't see any of them being hydrogen. What's the symbol for hydrogen?
H.
Yep, exactly, H. So I don't see any H in here. Then I look here, oh, there's H. That's H gamma, there's H beta, there's H alpha. Those are hydrogen. So this can't be a type 1 supernova. This is a type 2. As soon as I see hydrogen in there, I know that it's a type 2. Down here, there's some different elements, and you'll talk more about what those elements are in the breakout rooms, but none of them are H, so that must be a type 1. So if you're here, I'm not seeing any H, all right, that's a type 1. So that's how I tell the difference. If it's a type 2, there's hydrogen. If it's a type 1, there's no hydrogen. That's how I classify them there. Okay, so we're getting ready for your turn. This is the scenario that I'm setting up. You have gotten a gravitational wave alert from LIGO. You're on the LIGO email list, and they send out an email, say, all right, we detected a gravitational wave event, and it's in this region. And then you've used your telescope and you've searched the sky for transient, for new things. And so now you have both images and you've gotten some spectra. So first you're going to try to find the transient. You're going to try to find the new objects in the images. That's your first job, is to find the new object. And that will involve searching through lots of images. I'm just going to give you a couple, but in reality, it's searching through lots and lots and lots of images. And really, you're going to use a computer to do a lot of that. Once you find the new object, you're going to look at the spectrum and try to decide, is it a kilonova or is it a supernova? So what to do, you're going to compare images, either top and bottom or left and right, and you're going to see where's the new object, where's the fairly bright new object, the thing that changed. That's what we call a transient. Transients can be all kinds of things. Then you're going to mark it with an arrow, and then you're going to use the spectrum to decide if it's a kilonova that we're looking for or a supernova. Here's a decision tree for you. So if you look at the spectrum, if you see dips or bumps in the spectrum, if yes, then it's a supernova. If no, then it's a kilonova. If you get to yes, it's a supernova, then you have to ask, is there hydrogen? If yes, it's a type 2 supernova. If no, it's a type 1 supernova. So this is how you're trying to tease out this information about what type of object it is. All right, so this is where we're going to start. We're going to practice with this. We're going to look at an image of this galaxy. This really pretty galaxy called M51. M51 is a spiral galaxy in a constellation called Canis Venatici, the hunting dogs. So you're going to look at this galaxy, and then so here are our images. You're going to get a series of these images when you go to breakout rooms. This is our first test. We are going to be, on the left is a template image. So that's an older image of this galaxy. On the right is an image that we got more recently, and there's a transient in it. There's a new object in it. So your job right now is to stare at the two images and try to find the new object on the right. Then let's give it a shot with putting an arrow next to it. When you find it, go ahead and let's try to put the arrow. So again, you're going to go to viewing options, and then
Sure. You'll up at the very top where it says you're viewing Matthew Wiesner's screen. There's a little box that says view options. You click view options, you go down and select annotate. And then you'll see a little menu at the top. And you're going to look at the third one from the left where it says draw. And you're going to go down and select the arrow. And then when you go to the screen now and you draw an arrow, I'm just going to draw it and show what it looks like. You click, draw, drag your mouse and let go, and there's your arrow. Now, you can't move your arrow, so you're going to aim it toward the spot that you think is the object, the transient. Yes.
I don't have that option. The only option I have, it says original size and enter full screen.
So we'll follow this up in the smaller groups, but I'm seeing a few arrows here, and you notice what they're pointing at is that object on the right that's bright, that's not present in the image on the left. And what that suggests is that was a new thing, that was a transient. And that could be a supernova or a kilonova. So if we were trying to follow up gravitational waves, if we found something like that, that could be the kilonova. So what they're pointing to, that is the new object. So that's the transient. So good job, you found the transient. That's the first step, is to go through lots and lots of images and try to find the transient. The second step then is to say, all right, we found this new thing. What is it? And so then here's the spectrum for that exact object. And so we look at this spectrum and we ask ourselves, we go think about our decision tree and we ask ourselves, are there clear dips or not? What do you think? Do you see clear dips here? Yeah, it kind of seems like it, because it's going up and there's a big dip there, there's a dip there, there's a dip there. All right, so this is not a kilonova because we have these absorption lines, these really clear dips in the graph of the in the spectrum. So this is a supernova. So we've now answered the question, this transient we found in that galaxy is a supernova. Our next question, is this a type 1 or a type 2? Well, we're looking for, yeah, go ahead, what'd you say?
Type 2.
And how did you decide that?
Because you can see in the middle of the screen it has hydrogen.
Absolutely, that's it. So there's hydrogen in the spectrum, so it has to be a type 2 supernova. There you go, you classified the object. So now you have information about this object. It's not the kilonova, the colliding neutron stars you were looking for. This is a type 2 supernova, which is going to be a massive star that collapsed on itself and exploded. All right, so we're going to go through and try. So this was a type 2P. So this is our summary. So we can use light and gravitational waves to learn more about things in space. After LIGO finds gravitational waves, we go out and try to find the new object, the transient. Once we find it, we try to decide if it's a kilonova or a supernova by looking at the spectrum. Many of the objects we find turn out to be supernovae, so we need to be able to tell the difference. And then we want to classify them. Are they type 1 or type 2 supernovae? All right, so now it's going to be your turn. And yeah, so I'm going to stop sharing here and you are going to head into breakout rooms.
Okay, let's, Amelia, let's go ahead and go to breakout rooms.
So first, let's make sure this works real quick. The annotate thing, because a couple of you were having some troubles with it. So if you guys like jiggle your mouse, you see the, like you are viewing Gabriel Goodwin's screen. Can you guys all see that right now? Yes, okay.
Gabe,
Right next to
Gabe, do you want to go full, like go to projection mode or presentation mode on your slides?
yes, I can. Real quick. Okay, that should be working, right?
Yeah, perfect, great.
Awesome, awesome. All right, so in the menu where it says like viewing options, it goes to annotate. You all able to draw stuff on the screen? Like I'm just drawing an arrow right now. Are you guys able to see this and draw for yourself? Okay, so one person is. Awesome, okay. Let's get started then. All right, here's the first object. Let's think for a couple of minutes where this could be. All right, do you guys see it? Do you think you might know where it is? No?
Gabe, I think this is a tough one.
Yeah, this is probably the toughest one.
I think we're starting with the most difficult one. So
yeah, I agree.
There should be an object, a transient, in the right image that we don't see in the left image, right?
Yeah.
So try and maybe look in this region.
Baha, that's a good suggestion. The transients are most likely going to be closer to the galaxy than further away.
All right, I see one of us is already finding it.
So this is this guy. These are in both images. This one's in both images.
Yeah, I can't see the name anymore, but whoever's arrow just got erased. It was over this object right here on the Kindle. So yeah, that is
there we
the
go.
object that's different. So all right, so we found the object. Now we have to figure out what it is. So this is our spectrum. I'll clear these other images real quick. All right, once one of you thinks you know whether or not it's smooth or jagged, just unmute and let me know.
I think it's a type 1 supernova.
Why do you think that? Real quick.
Because it has a bunch of ups and downs and it doesn't have hydrogen in it.
Yep, that's exactly what I'm thinking. So yeah, it's jagged, so it's not smooth, which means that the light is passing through a bunch of atoms, which means it's not a kilonova. And then from the absorption peaks that we're seeing right here, it corresponds with a ton of metals, like you can see calcium and silicon and magnesium and iron, but not hydrogen. So yeah, I would agree with you that it's a type 1 supernova. Yeah, good job. Sorry, you go ahead, Baha.
Just you both have it.
Yeah, so you guys found it. It's right here. This is the big difference between them. But I mean, doesn't it look like there are tons of more stars in the first image than the second one? Why do you guys think that could be? Like why there are so many more stars in the first one than the second one? Okay. So a lot of the times when you're looking for transients, you're taking multiple images, like several images at a time with a little bit of like time spacing between them. So these photos were probably taken somewhere between a few days apart and a couple weeks apart, just to see if things are actually moving or not. And a lot of the time, smaller things like weather conditions or just even the brightness from which you're taking the image could like make a lot of the difference. So that's kind of why you're seeing a lot of new stars or a lot of stars in the first image, but the photo almost looks to be a little bit darker in the second image. So
how do we differentiate between whether something is actually a supernova like we're doing right now, or a kilonova, versus whether it's just some disturbance that we're seeing in the image?
Does anyone want to take a guess real quick?
We're kind of already doing that, right? We're looking at something related to that supernova or kilonova that other objects that are just disturbances wouldn't have, right? And that's the light spectrum that we're looking at, right? They're characteristic and we know what they should look like. That's what we see, right? So that's how we're able to tell, oh, that's something that's actually interesting that we can look at.
Yeah, exactly. We could, like, for all we know, if we didn't like look at the light spectrum at all, this object could be like an asteroid or something. So that's why we really need to do other things like look at the light spectrum, so that way we know.
And also we get, the main topic is multi-messenger systems, right? So we also got a signal that there is some big gravitational disturbance in that direction. So that's what we're also kind of focusing on.
Yeah. All right. so here's a spectrum. When one of you guys thinks you know what it would be, just shout out what you think.
I think it's a type 1 because it's pretty jagged and has no hydrogen. Sorry about that.
Yeah, no, I think the same. What about you, Jack or Brian? Yes, I'm seeing you shaking. I'm seeing you nodding. So, yeah, exactly. This is also going to be a type 1 supernova based on all the metals that we're seeing being absorbed. All right. Any questions before we move on to object 3? Nope.
Now, do you guys think this is a supernova or a kilonova?
I think it's a kilonova
How come?
because it's like there's no clear dips that you can tell that are there.
Exactly correct. All right. Let's move to the next one. Where do you guys think the transient is?
In the left picture, there's like a dot in the thing, but it's not there anymore on the right side, or at least it moved. If it did.
Braden, I think we have
Was this one flipped?
discrepancy here. I think these images are reversed. I think
Okay.
the transient is actually in the left image and not in the right image. That would be my mistake.
That's what it looks like. Yeah, that is most likely it.
I think we're on the right track now.
And do you guys think this is a supernova or a kilonova?
Supernova.
I do too.
Good job. That is right. Now, what kind of supernova?
I think it's a type 1.
I agree.
Correct. Type 1 did not have hydrogen. All right, here's our next one. Now, this one is a little different. We're going to flash between the two images and tell me where you think the transient is.
Yeah, where the arrow is.
Yep, that's exactly right. Now, which way do you guys think was easier? Do you think it's easier to flash between them or look at them side by side?
I think it's easier to flash.
I would agree because you can see what shows up.
Definitely. And the way that astronomers typically find these is you'll use computers to align the images, and then you'll do a subtraction, where basically you take this original image and you subtract everything from the new image and look at the differences. That's kind of what you're doing when you're flipping between them. And that's basically how astronomers find transients. Typically, it's done with a lot of machine learning, though it's typically not done by eye. When you find events that you think are, you definitely look at it by eye, but there's a lot of data that has to be sorted through. All right, do we think that this is a supernova or a kilonova?
Supernova.
I think it's a supernova.
You're correct. Now, what type do you think it is?
I think it's a type 2 because there's hydrogen.
I agree.
Yep, that's exactly correct.
We have a few minutes actually before we go back to the main room. Does anybody in the room have a question? How about our TAs? Do you want to just give us a little bit of history about who you are and what you do and where you came from and why you're in physics?
Sure. So I've basically always been interested in science since I was a kid, like a lot of people, specifically astronomy. So I decided to come here and major in physics. I think physics is the most interesting of all the sciences personally. You get to really learn about the fundamentals of why the world the way it is. In many ways, you can think of other sciences as kind of like derivatives of physics. So in many ways, chemistry is kind of applied physics.
It's just been 6 months since I got to the US. I'm originally from India. So I immediately joined the astronomy group. And fortunately, I met Dr. David, and he has given me the opportunity to be a part of the Saturday morning astrophysics group at Purdue. So by doing and also as a part of the astronomy club and all these, by doing all of these activities, I always feel I have the strong grip on astronomy, even though I'm studying aerospace. I personally feel subjects like aerospace and astronomy will give us the answers about why we are and what is our next step in this galaxy or wherever we are. I've always been curious about these questions, and I just thought maybe pursuing my education in them will give me the answers for these. Pretty much that's it. Thank you.
Now that we're all back in the main room, Professor Wiesner, do you want to wrap up with any comments that you have to say?
I do. So I just wanted to quickly run over each of the objects. So let's play. And there we go. All right, object one, I think everybody found this right here. There's the transient right there. This is called supernova 2011 FE, and it was a type 1a supernova. So that's one of those white dwarfs that got too big and exploded. Object two, I think you found that it was this object right here. And this is the name of it. It's named after the survey called Ogle. And it is this was a type 1a. And object three, there you go. Object three was the kilonova. That was the big one. I didn't show you this picture when I was talking about a kilonova to not give it away, but this is NGC 4993. That's the name of the galaxy. And this was the kilonova that when we found those gravitational waves in 2017, and then we went searching for the transient, we found it pretty quickly. And lots of telescopes were looking at this. So this is showing how the brightness was changing over time. You can see it got really bright at first when the neutron stars hit each other, and then it got dimmer over time. And we also took spectra, and we were able to tell that that was the kilonova. Object four, you saw that it was right here. This was supernova 2014J in a galaxy called Messier 82. And this was a type 1a supernova, another one of those exploding white dwarfs. And then the last one, you saw this, how powerful it is to flash back and forth between two images. This is a technique that's been used for a long time in astronomy. In fact, that's how Pluto was found, was by Clyde Tombaugh flashing between two images and seeing that something had changed between them. So objects in the solar system will change too, and that's not because they're getting bright like a supernova, but because they're moving really rapidly. So this is also a technique you can use to find things in the solar system. So this was supernova 2013 EJ, which is a type 2 supernova, a collapsing massive star in a nearby spiral galaxy. All right, so that was a great activity. So we're getting ready, those of us who do this kind of searches for kilonovas, we're getting ready to do it again. So LIGO has been turned off for about 2 years now as they've been upgrading it. And we're getting ready in December of this year, they're gonna turn LIGO on again for about a year. And we're gonna be getting, I'm expecting we're probably gonna get somewhere around 100 gravitational wave events over the next year. And I have my fingers crossed that a few of those we'll be able to find light from too. So hopefully, if I give this talk in a couple of years, I'll be able to talk about like the 4 kilonovae that we found. So we're gonna be getting ready to be doing more of these searches and trying to find the transient after the gravitational wave event. So keep your eyes on the news. Starting in December, you're probably gonna see like gravitational wave found, black holes colliding with each other as LIGO is getting ready to turn on and find more events. So I will close it there. I love this quote from Einstein, that I have no special talent, I am only passionately curious. You always want to keep asking questions and wanting to know new things. So at that, does anyone have any questions?
I had one that I asked to the students in our breakout room, if you don't mind.
Yep.
So if you remember from the slide where you showed all of the spectrum for the absorption and emission, it was very sharp. Like there were actual lines that you could see, and sort of dips and peaks in the graph. And I was just asking, why is that?
So this one?
Yeah.
Okay, so why are they really, really thin like that?
Yeah.
Yeah, so the width of spectral lines is determined by a number of things. And one of those can be how fast things are moving nearby there. It can also be how hot it is. So as they get spread out, one of the things that can happen is what's called the Doppler effect. The Doppler effect can make wavelengths be slightly longer if they're moving away from you, or slightly shorter if the source of waves is moving towards you. And so you can end up with this range of wavelengths for the same absorption line. And so it actually spreads it out a little bit. So there are a number of things that can cause that, but it tells you something about, for example, it can tell you that things are moving very rapidly or it's very hot at the place where this particular absorption line was emitted. It can also tell you about the surface gravity. You can get some information about how strong the gravity is there by the width of the spectral line. So basically, there's a lot of information you can get from that about why exactly they're so wide or why they're so thin. I see a question from Harrison. When do you think Betelgeuse will go supernova? Is it supposed to soon? So it was dimming recently, and we thought that it might have been getting ready to go supernova. So Betelgeuse is in, does anybody know what constellation?
Orion.
Good. Betelgeuse is an upper left star in Orion. And if you go out at night and find Orion, you find the belt of Orion, find the upper left, you can see it's red. It's a red giant star. So you can see that it's red. And it probably will go supernova. So that would be a type 2 supernova because it's a collapsing massive star. We're not completely sure. It could be really soon. It could be in next year or two, or it could be 1,000 years from now or more. So we don't have a good understanding yet of being able to predict very closely, but we know it's in the late stage and of its lifetime, and it may go supernova soon. So that's one we'll just have to keep an eye on. Good question. Any other questions?
I have a question. So you said that you've only found 1 kilonova. Do you mean 1 kilonova with both light and gravity, or 1 kilonova of all? Because I would guess that, large scale surveys would probably find quite a few just in light.
That's true. So so a kilonova refers just to light. So you can get information from the gravitational wave. You can get information about the sizes of the objects. And so we have seen other neutron stars colliding with things. So there was one we followed up 2 years ago where there was a neutron star that collided with a black hole. And it's possible that could produce a kilonova. And so we were hunting for a while to try to see if there was a kilonova, the light that comes from it. We never found it. So there have been other neutron star related gravitational wave events, but we have not found light from any of them. Now, the other thing with these events is they also produce bursts of gamma rays. And I know that's one of the focuses at Purdue is high energy astrophysics. And so there are searches involved also at Purdue to try to find gamma rays from particular objects. And so these events can cause gamma rays. In fact, the kilonova GW 170817, the one kilonova we found, it also produced a burst of gamma rays. So that's another piece of information. It's still electromagnetic radiation, it's still light, but that's the really, really short form of light, the really high energy form of light. So we've also gotten gamma ray bursts from various objects, and so those might actually be kilonova, but we didn't actually find the light, the visible light from them, so we haven't called them kilonovae. So you're absolutely right that we're expecting to find a bunch more of these, especially as big telescopes like LSST start to, at the Rubin Observatory, that as they go online and we start to get lots and lots of new information, we're expecting to find a bunch of these things. So we're thinking hundreds, maybe, if we're lucky, somewhere in that range, like 100, something around there over the life of the survey. They're still rare, but we think we're going to be finding more of these as we go into the future. Thank you for that question.
I have a question.
Yes.
So when Betelgeuse will turn into a supernova, are we going to observe that like a constant small firework that is twinkling in the sky?
When Betelgeuse goes supernova?
Yeah.
Yeah. So it's not gonna be varying over like a minute or two. It's gonna just be a really bright star. That's what you would see. It will go from the red giant, the kind of bright star we see now, to a really bright star. And then if you keep coming back night after night, it'll be a little bit less bright, a little bit less bright, a little bit less bright. It's over a couple of weeks that it would dim down back to not too much more than it was. So it'll be really spectacular. I'm expecting it will be this really bright star out there. There have been the one that formed the Crab Nebula 1,000 years ago, I'm told they could see it in the daytime, that it was so bright. It was like the full moon. It was so bright that it was totally stood out at night and you could actually see it in the daytime. So for really near supernovae, which are quite rare, they can be really, really extraordinary events in the sky. So what you'll see is very rapidly, it will become a much brighter star than it was before. And over the next couple of weeks, it'll dim down over time. So hopefully it happens in our lifetime. That would be really, really cool to see.
Yeah. So when you say bright as Sirius?
I expect it'll be brighter than Sirius, yeah, when it goes supernova.
We're about out of time. I want to ask one more question, if I may. Supernovae and kilonovae are both violent events. They both produce light. Why do we see an absorption spectrum from the supernova when we don't from the kilonova?
That's a good question. And so the kilonova has a lot. Basically, it's producing so many spectral lines that they're kind of morphing together. So it is producing absorption lines, but you're getting so many of them that you aren't able to actually distinguish. It produces a lot of, in such an event is that you get a lot of heavier elements, because you're taking something that's really, really dense versus a collapsing star. You're taking neutron stars that are colliding, and you're getting these really, really dense things. And so you get a lot of absorption lines that kind of morph together, and so you can't really distinguish which of these heavier elements that you're getting.
Okay.
Yeah, so it would take quite a bit more effort to try to figure out which heavy element that is that you're getting in there.
All right. Well, we're at an hour and 20 minutes, and I think we should probably wrap up. We will take another question if any of our students has a question. Speak up, raise your hand. And in lieu of that, I will thank you all for coming. I think this has been a really good session. Professor Wiesner, thank you.
Thank you for having me. This was a lot of fun. Thank you, everyone, for coming.